All right, so now let's extend that idea of calculating center of mass from just talking about individual particles to actually talking about an extended body. So remember that to calculate the center of mass position, boy, you can't see that at all, can you? Let's try a different marker. To calculate the center of mass position, right, if we've got discrete particles, we're simply going to add up the mass-weighted positions of every particle and divide by the total mass of the system, right? And you can sort of think about how you would extend that to a continuous system, right? Instead of doing a discrete sum, you're going to do an integral over the domain of the position times a little chunk of mass divided by the integral of the domain of each little chunk of mass, right? So conceptually what we're doing here is simply going to each point in some domain, and we're asking the question, how much mass is located at that point, and what is the position of that mass, plus how much mass is located at this point, and what's the position of times the position of that mass, plus how much mass is located at this point, and what's the position of that mass. We're sweeping over the entire domain when we do that integral, and then we're dividing by the total mass. So to show what that looks like, let's do one example of that that's just very concrete. And the example that I want to do is a simple one. So we've got a triangular domain, right, that extends from 0 to L in the x direction and 0 to L in the y direction. And it's a two-dimensional domain, so it's like a plate of metal, and that plate of metal has a surface density sigma kilograms per meter squared, and I'll just assume it's a constant surface density. So what we want to do is figure out where the center of mass is for this object. Conceptually, that center of mass ought to be the point at which you could balance the object on your finger. So if you think about this object, you'd sort of imagine someplace around here is where you'd be able to balance it on your finger. Let's see if the math shows us that. To define the center of mass for this, right, I want to do the integral over the domain of the position vector times dm. Well, the position vector, let's actually think about what the domain is first. So x is going to run from 0 to, let's actually do y first, and we'll do x. X runs from 0 to L, right? And then y actually runs from 0 just to x, right? Because when x is 0, I don't go very high. As x increases, I'm going to go higher there, right? So that's what my domain is going to be, is integrating from y equals 0 to x and from x equals 0 to L. My dm is simply going to be sigma times dy dx, right? That's dm. And then my position vector is simply going to be x times I hat plus y times j hat, right? So conceptually, when I do this integral, I'm sweeping over all y and x values, and I'm going to each combination of x and y values and asking the question, what is sigma times dx dy of this? Okay? I'm then going to divide that quantity by the integral from over the same domain of simply sigma dy dx. Okay? So that's the calculation I need to do. Now, I know what this bottom integral would better give me, right? Because this is simply what's the mass of the lamina, right? So I've got a triangle. The triangle has an area of L squared on 2, right? L squared on 2 times sigma should be what the mass is. And indeed, when I go ahead and calculate this, right, my first integral gives me a sigma times x. The integral of sigma times x dx from 0 to L is L squared on 2 times sigma. Sure enough, when I do this bottom integral, this is the answer I get, right? But let's do the top integral as well, because the top integral we need to think about a little bit more, and it's a nice example of doing an integral that actually involves using vectors within the integral, right? So my position of the center of mass is 1 divided by L squared on 2 sigma, right? That's what the bottom part of this expression comes from, right? Times the integral from 0 to L, y equals 0 to x, of xi hat plus yj hat times sigma dy dx, right? And what I can do now is actually, this is an integral of a vector quantity. I can actually pull out, sort of break the integral up and pull out the I hats and the j hats and get, let's do the I hat component first. So I'm going to get an I hat times the double integral of x times sigma dy dx, right? From y equals 0 to x equals 0 to L. And when I do that, this integral, well, let's see, the first integral, I'm integrating this with y, so I get sigma times x, so I get sigma times x squared from the first integral. When I do the outer integral, I'm integrating sigma times x squared from 0 to L, so I'm going to get sigma times L cubed on 3, right? That's what my I hat integral is going to give me. I've also got a j hat integral, right? That integral is going to be j hat times the integral from y equals 0 to L, or sorry, 0 to x equals 0 to L of sigma times y dy dx, right? And when I do sigma times y dy dx, right, when I do my integral and inner integral, I get sigma times y times x, right? Or sorry, I get sigma times y times x squared on 2, right? And when I do that, the outer integral from x equals 0 to L, that x squared on 2 will give me an x cubed on 6, right? So this integral actually gives me sigma times L cubed divided by 6 j hat, right? So if I actually now go ahead and take both the denominator and the numerator, let's see what I get. Let's see if I can actually get that all on the screen. There we go. Okay, so pretty clearly my L squared is going to cancel with the L cubed, leaving just an L on the top. My sigma is going to cancel with the sigmas. So, and I'm going to get an L divided by 3 times 2 in the I hat direction, right? Because this 2 is going to come up into the numerator, right? Plus an L divided by 3 j hat. And I'm not doing all the algebra for you, but that is what the answer comes out to. And we can look back at our original diagram and ask, does that actually make sense? And sure enough, my center of mass is 2/3 of the way in this direction and 1/3 of the way in the j hat direction, right? There's my center of mass.